Good morning, good afternoon, good evening, everyone. Thank you very much for attending this presentation. I'm fully aware about differences in time zones, so thank you so much to those that stayed awake very late in the evening to listen to me today. Also, I would like to thank today Enrico for his kind introduction to give this talk, and of course the RILEM Association for awarding me, well, the Robert Lemid Medal 2022. So for me, it's an absolute honor and a pleasure to be delivering this lecture today. So I will give you a brief flavor of some of the things that I've been doing throughout my career regarding understanding of the durability of cementitious materials. By the way, I'm Andrea Bernal Lopez. I'm professor of structural materials in the School of Civil Engineering at the University of Leeds. So perhaps I'm here preaching to the converted, but we all might agree that restore and improvement of urban infrastructure is one of the key challenges of our generation. So the National Academy of Engineering in the US has identified this as one of the 14 grand challenges of engineering in the 21st century. And the main reason to do so is, of course, that infrastructure is the lifeline of our way of living. However, climate change is posing tremendous challenges to our built environment. So it's not just about the impact that construction or infrastructure have in our natural environment. Also, we need to bear in mind and take into account that changes in our climate would also affect tremendously how particularly our cement and concrete based infrastructure is going to perform in the years to come. So here I'm just showing some different scenarios about changes in climate, temperature, if we carry on business as usual, which I think is not an option, or if we take some conservative approaches, or if we take the radical approaches to climate change that are urgently needed. So thinking as a concrete technologist or as a cement chemist, we can see how these different environmental exposure conditions might perhaps exacerbate some of the degradation mechanisms that we all understand are likely to happen in our built environment. These are just some examples of how climate change is calling for more resilient infrastructure to the tremendous effects that it can have in our way of living. So these images are not just one in a lifetime events. More often we're seeing images like these all across the globe where our built infrastructure is put to the test. So we're really facing here not just the challenge of climate change, but also the challenge of making our built environment capable to endure and overcome these tremendous changes in climate that are occurring at the moment and might occur in the future. At the same time, there is a growing interest, of course, in the infrastructure sector to become more sustainable, adopting low carbon technologies, low carbon materials, so on and so forth. But also there is a growing interest on adopting some of the concepts of circular economy, reduce waste of materials, maximize the reuse of buildings or structures to reduce a consumption of virgin materials in the longer term. However, for us to transition to a circular economy in the infrastructure sector, we need to bear in mind that concrete must be durable to enable its reuse and repurpose beyond the original design life for a specific structure. So we cannot divorce the concept of sustainability from the durability of the materials we're going to use. Because if our concrete is no longer performing as we wanted it to perform, why will we reuse it for a new structure? The other thing is we need to think about this trade-off or this balancing act almost between the service life of structures but also maximizing their potential CO2 uptake during a lifetime, considering that this recarbonation concept is gaining more and more force all over the world as a way to balance the potential CO2 emissions that are allocated to the production of cement and concrete. In terms of perspectives, at least in the UK, an independent review of the construction sector has revealed that the construction industry has been described as not fit for purpose in the face of the current challenges in terms of performance, in terms of resilience, in terms of sustainability. So this is a wake-up call for us to think about different ways to enable transformation. So one of the first things is rethinking the relationship between nature and the built environment. So we need to think that the built environment is our adaptation to the natural environment to suit our social needs. Therefore, we need to find a balance between built and natural environment and harmonize the way both are protected and the effect of one doesn't affect the other. The other thing is organizational change. We need innovative ways to reorganize the perception of a given infrastructure project. So we need to move from thinking just about the material, just about the design, or just about the purpose of a specific infrastructure individually. And we need to think about how, in a systems approach, globally thinking, how each of these steps of the process might affect the long-term performance and longevity of that specific project. And also, there is a lot of work being done at the moment in terms of should we change the way we produce different sort of materials, or we even construct our buildings and infrastructure? What is the best technological choice? Do we need new technologies? Can we use the ones we have? Do we need to continue growing? So those are some of the key questions that we need to ask ourselves thinking about leading transformation. So, as many of you might know, of course, the focus of the majority of my research, of my professional career, has been on the development and assessment of low-carbon materials, specifically alkali-activated cement. So in this image, I'm just showing how alkali-activated cements compare in terms of chemistry to Poland-based cement and also calcium sulfonaminate cement. So what is important is that alkali-activated cements have proven again and again their ability to produce materials that can enable environmental savings, at least at their production level, between 40 to 80% compared with other technologies. The reason being that the majority of raw materials used to produce alkali-activated cements are waste or byproducts from different processes. Also is a chemical reaction that can take place at room temperature. And also we have discovered over the years that we can tailor the properties of these materials to be advantageous, for example, for specialized applications such as fire resistance or nuclear waste immobilization. However, when we think about a given piece of cement or concrete, we cannot divorce that from the environment when it's going to be placed. So the concept of durability is not absolute in terms of link to the longevity of specific structure. It is intimate interlink between the material properties and the environment where that material is placed and is going to serve during a lifetime. So this is an image that I use often in several of my presentations, and well, all credits to John Provis that designed it, because this shows the huge complexity when we think about the correlation between the concrete and the environment. So many things can go wrong because there are so many aggressive agents that once enter the material can induce significant changes and perhaps compromise the long-term performance of the concrete. So my presentation today is mostly going to be devoted to carbonation of cement and concrete. This is a topic of research I've been very passionate about. It was the main topic of my PhD dissertation back in the day, and I've been working on it for over 15 years. And of course, some of the motivations for me to work in this area and find it really fascinating is, of course, I want to understand how the carbonation of concrete can affect the longevity and the performance in the longer term. But also because I believe that a material to be sustainable, it needs to be durable. And CO2 is present in the air. The CO2 concentrations in the air are the highest in human history. So it's one of those aggressive agents that will be present in any infrastructure that we develop. Also, what interests me now is that performance-based approach standards are being favored for enabling adoption of novel cement and concrete, which I think is the right approach. However, for us to truly understand the meaning of the outcomes when we test novel cement and concrete using the same testing methodologies that have been developed for Poland cement systems, for example, we need to know what the mechanisms of degradation of those cements are to be able to say, yes, a performance-based approach is suitable for these materials, or yes, this performance-based approach will suggest that this material can be used when tested under these conditions, but perhaps those are not the right conditions to be testing the material. So it's an open question that I have for myself, if I'm very honest. And this is why I'm also very interested in understanding mechanisms of degradation of cement concretes. And finally, and I will say with a little bit of concern, is that the recarbonation of concept or the ability of cement and concrete during the service life to uptake CO2 is a concept that is getting more and more acceptance, I will say, in a national level, at least in the UK. And I will say concerning is because, of course, the concept of recarbonation is being accepted thinking about carbon tax, potential statistics of air quality and pollutants. And the thing is, how can we truly determine the level of carbonation or the ability of a given concrete to uptake CO2 during a lifetime of service? So I think the concept is really valid, but at the same time, I'm a little bit careful thinking about how any quantification can be done in a conservative way, so we don't overestimate perhaps the potential of carbonation in terms of CO2 savings in the longer term of cement and concrete. So today also I want to talk about carbonation of alkali-activated materials. So I started working on this topic during my PhD, inspired by the fantastic work that was being developed by the Eduardo Torroja Institute in Spain, particularly by Marta Palacios and Francisca Puertas on this particular topic. When I started working on this, very few studies were reporting carbonation of these materials, but what was really interesting to see is that we were trying to solve this problem or understand these mechanisms of degradation in the same ways and using the same tools and perhaps fundamental knowledge that we have for Portland cement systems. At the time, I remember that I became interested in this topic because everyone used to say, oh, alkali-activated materials carbonate far more than Portland cement, therefore they are not durable, therefore we shouldn't be using them, we should not be studying them. And I remember always wondering, but why is that? And at the time was very little information, so I dedicated a long time, a lot of work during my PhD trying to answer some of those questions, and I will say as any good PhD work, I came out from that project with far more questions than answers. But what is really important to mention here is that we cannot universally say that every alkali-activated concrete will carbonate more than Portland cement-based concrete or blended Portland cement concretes. I will show later in my presentation that that's not the case, that there are many factors that will influence the performance of these materials, and therefore we cannot generalize. And I'm saying this not just for alkali-activated materials, but for any other non-Portland cementitious system. Differences in chemistry and microstructure of non-Portland cement systems means that it's very likely that the degradation mechanisms linked to durability of these materials are quite different to what we know and understand for Portland cement, which also opens a big question of how we can test them. So back in the day, when I was trying to answer why the results from my PhD are so different to the results that colleagues from the Eduardo Torroja Institute were getting, and also some of the results I was collecting when I was a postdoctoral researcher working with Gianni van de Vente in Australia. So I was very fortunate that at the time Gianni was very active in RILEM as well, and I became involved in this, and I saw the fantastic work that people could do when was working together with people from all over the world. So that inspired me to contact all my colleagues in Colombia, in Spain. Of course, I was working in Australia at the time, and say, can you please send me some samples of your slag? And then for the first time, I could sit down with samples coming from different parts of the world, treating them exactly in the same way, exposing them to the same environment, and see what happened. So this, I will say, was a milestone scientific point in my career, because when we did this study, we managed to identify that one of the key differences in the three slags that I was studying at the time was the magnesium content. So the Spanish slag was very standard for European slag. The Australian one is fairly standard for Asia. The Colombian one is quite unique type of slag that unfortunately is no longer produced with this sort of composition. But at the time, this study let us identify how the magnesium oxide content of slag has a tremendous impact, one, in the chemical composition of the catch phases that are forming in this type of materials, and second, in the secondary phases that can form, particularly the formation of layered double hydroxides or hydrotalcite, which can act as CO2 solvents within the material. So we identify in this study how, as we increase the content of magnesium oxide in the slag, we can certainly reduce the carbonation of the material. So these also demonstrate that not all alkali-activated slag cements will carbonate in the same way. So a lot of studies were done in that area. many published papers were also out there. But then the interesting part was that understanding what was influencing the carbonation of alkali-activated cements enabled us then to use the same principle but studying a complete different chemistry. So when I relocated to the UK later in my career, I realized that a lot of the comments I was getting during my presentations about alkali-activated cements were regarding the potential global warming effects of the activator, the safety concerns of using highly alkaline activators. So I started working on near neutral salt activated slag cement. I still work actively in that area. And one of the most promising ones was sodium carbonate. So I started digging on the literature. I realized that early work in Ukraine was being done with sodium carbonate. They produced it successfully railway sleepers with this type of activator, and I was wondering why no one else was able to make it work. What's influencing this? Why everyone says sodium carbonate activated slag cements don't harden, they don't work. So once again, with the fantastic Xinyuan Qi, this is the work during her PhD, we start looking at different slags and activated with sodium carbonate. And once again, we identified that there was some sort of correlation between the slag composition, particularly the magnesium oxide content, the kinetics of reaction of these cements, and of course the phase assemblage evolution of these cements as well. So what was really interesting is we identified that as the magnesium oxide content increased in the slag, we favor the formation of this layer double hydroxide hydrotalchides. And it seems like the in situ formation of these phases somehow enables the consumption of the CO2 that will be present in the pore solution of these systems, and therefore that will speed up the process of reaction of these materials, because the pore solution will be very similar to what we can expect in a sodium hydroxide activated slag cement. So I will say this was another nice discovery, because for the first time in many years we could demonstrate that sodium carbonate activated slag cements could be produced, that we needed to select the right material for the right activator. So not all activators are suitable for other slags, but we could also potentially develop materials with improved durability. And this is exactly what we did. Again, this is the work of Xinyuan Qi, where we exposed to carbonation sodium carbonate activated slag cements. So the formation of this layer double hydroxide has like a double effect. It helps to control the kinetics of reaction. So now we were able to produce cements that will harden within expected times with desirable compressive strengths, as you can see here. But also, this particular type of systems seem to be more resistant to carbonation than any other alkali-activated cement that we evaluated before when we use sodium silicate or sodium hydroxide activator. So we can see here that the materials is still carbonating. This is in the blue line. However, the compressive strength is not changing, which I will say is the ideal outcome. We want our materials to absorb as much CO2 as possible, but we don't want that carbonation process compromise the performance of the materials that we're producing. So this is just to give you a flavor of how understanding the mechanisms of carbonation, discovering some of the factors that influence how the materials perform, or why the materials perform in a certain way, enable us not just to find strategies for us to improve carbonation resistance, but also to design materials with the desirable properties that we're looking for. So of course, we did some studies adding some nano synthetic layer double hydroxides to validate all these concepts. And well, we were very fortunate that the results demonstrate that we were right, at least in theory, about the performance and the key role of the secondary reaction products on carbonation of alkali-activated materials. But of course, that sounds fab, but then it opened more questions than answers, because we say, okay, now we know that we change the slag chemistry, everything will change. If we use a different activator, everything will change. But what we're craving for the widespread uptake of this technology is presenting some guidelines or universal guidelines that enable people to design these materials in the right way so they can get the performance that they desire to obtain from the material. So we did some thermodynamic modeling. So we continue working in this area. So these are some thermodynamic modeling simulations of carbonated sodium silicate and sodium carbonate activated slag cements. And I will say at the time these were the closest to what we were seeing in experiments in terms of simulations that we could produce, which I think also enable us to understand more and more about how things happen. So of critical importance perhaps for that people that is very interested in the correlation between carbonation and corrosion of steel rebars is identifying how the changes in phase assemblage as carbonation progress might influence how the pH is changing over time. So it's a two-thing situation. If we lose the binding phases in our material, the strength-giving phases in our material, but the pH is still high, is kind of irrelevant up to a certain extent. So what we're looking for is to conserve the majority of our strength-given phases before we reach a pH that could destabilize any oxide film that can form in a steel rebar here. But what is important is that this thermodynamic modeling approach enables us to predict which type of slags with certain composition are more prone to carbonate more than others when they are activated with certain activators. So it enabled to do a quick scanning of what will be the best or potentially the best activation conditions to produce a material that will be resilient to carbonation. But we know that carbonation is not just a chemically controlled mechanism, it's also a diffusive control mechanism. So there is tremendous interest, of course, to understand the pore structure of this type of materials. So in this opportunity, these are micro CET reconstructions for blended Poland cements with high volumes or blast furnace slag as a function of curing time. So these are not exactly for alkali-activated materials, but I just wanted to show these beautiful reconstructions by James Biger that also has been working with me and others for many years in this area. Because one of the most challenging things when studying cementitious materials is getting a realistic overview of the pore structure. So a lot of the testing methodologies that we use require preconditioning that might induce microcracks in the materials, or we cannot visualize how the pores actually distribute. But this technique is non-destructive, is very powerful, and enables us to see pore size distribution, tortuosity, and therefore calculate diffusivity of cementitious binders. So in the case of alkali-activated materials, now that we have this underpinning understanding of how things progress, we wanted to see, okay, now we need to scale this up. We need to bring the transport properties of a given alkali-activated material into the mix to see what's going on. And that's one of the key areas of research that I'm developing at the moment, also with a fantastic PhD researcher, Liang Ye, who's working with me at the University of Leeds. So pretty much the concept we're using at the moment is not very new. This has been proposed in many years, but it's like the shell or the unreacted core type concept. So what we are assuming is that we will have these different layers of carbonated material, with which each of these layers, which we are assuming will be different ages, will have a specific phase assemblage, a specific porosity or tortuosity, and therefore carbonation in each of these layers will occur in a different manner, accounting the two concepts of changes in phase assemblage for solution chemistry plus porosity distribution as the reaction progresses. So hopefully in a couple of years I will be able to share some of the outputs of this amazing job that Zhengliang is currently doing. Okay, so I don't have too much time left, but I really wanted to highlight some of the work that I've been doing over the years with some of the RILEM colleagues, because I will say I will not be where I am without the fantastic support I have had from the many RILEM friends and colleagues over the years in the different technical committees. But because this presentation is about carbonation, I just wanted to highlight that in the RILEM Technical Committee 281CCC, we have been thinking a lot about it. It has been fantastic work done over the past few years. So one of the most interesting things we identify is that there are so many different standards that could be adopted to evaluate accelerated carbonation, with the objective, of course, to somehow correlate that to the natural carbonation performance of a given concrete. And all these different standards suggest different exposure conditions that can be adopted. So for example, this one, we can use 3% CO2, 4% CO2, 20 or 50% CO2. So which one is right? It's very challenging to say, and it's one of the questions that this technical committee was trying to answer. So in an effort to try to see if there is a certain exposure condition or preconditioning of concrete that might correlate with the conditions that are being recommended by other standards, this technical committee developed a round-robin test to evaluate the resistance to accelerated carbonation of Portland fly ash, and blast furnace-like blended cement and concretes. I will say this work is absolutely amazing. It's not just because of the number of laboratories and countries participating in it, but also by the fact that this work was mainly done during the global pandemic. So I feel tremendous admiration and respect for all my colleagues that continue working in this particular area in such difficult times, and also sharing their knowledge with all of us, or some of us that couldn't participate in the round robin, was keeping us like motivated and together when we more needed it. But yeah, I would like to invite you to have a look at this paper, because I think it's very, very useful. And just to conclude my technical part of my presentation, we have also been looking at this technical committee of the carbonation of alkali-activated materials. So this paper was actually just accepted this week in Materials and Structures, and I really wanted to highlight it and invite people to look at this paper when you can. The reason being that this paper was a tremendous endeavor putting together a database of all published data on alkali-activated concretes and high-volume SEM concretes exposed to natural or accelerated carbonation. So the database is massive, but some of the outputs are really relevant, because this study demonstrates that the carbonation coefficients of alkali-activated concretes, or some of them, are comparable to those of blended Portland concretes that are currently used for many applications. So this demonstrate that premise that alkali-activated concrete cannot be used because they will carbonate more than the concrete we use now is not entirely true. What next for me? Well, I will say I've been inspired the past couple of years to move a little bit away from fundamental research and start thinking about how the research I do could be put to better use, thinking about cross-sectorial approaches, thinking about foundation industries, high energy or energy-intensive industries, and how different concepts or strategies to decarbonize different sectors could be shared across all of them. So I'm part of the Transforming Foundation Industry Network Plus in the United Kingdom. We collaborate with industries of 6 different sectors, and we center our work in resource recovery from waste, circularity of waste feedstocks, and opportunities of transformation. And also, I have become more interested in circular economy and how we can use these new cement and concrete technologies to minimize the use of natural mineral resources. So, of course, I would like to thank all the different universities, funding agencies, industries as well that have sponsored my research and have enabled me to do what I really love. I feel very privileged today doing this presentation because I do what I love, and I've been having a lot of fun over the years doing research in different areas. So, of course, without this funding and this support, I will not be able to do it. And also, I would like to thank, I will say, RILEM, because all the different technical committees I've been part of throughout the years, and all the fantastic friends and colleagues I currently have, thanks to RILEM, have inspired me and have supported me, and I love how we learn from each other and we support each other. And I think that has been more visible over the past few years. Also, I would like to thank my family, because without their unconditional support, I would not be able to be where I am. And well, I would like to thank all the former students, current students, former postdocs, current postdocs, collaborators, and everyone else, from technicians, from secretaries, everyone that in one way or another has made a contribution to my research and to enable me to make my research vision a reality. So for many of you that perhaps like me at some point thought that you might never be able to be successful getting an award as important as the LIMIT medal, I just want to put this message here because I think it's really important that you're braver than you believe, stronger than you seem, and smarter than you think. So don't let anyone let you think differently. So thank you very much once again for your attention, and I'm more than happy to take any questions.